You know that moment when you see something ordinary, like, I don't know, the way colors swirl in a glass or how a rubber band snaps back, and you just get that little spark of curiosity.
That feeling of wanting to know how it works.
Exactly. That urge to understand the world around us, that's really what fuels us here.
Right.
And today we're taking that curiosity and really diving deep into a whole collection of fascinating scientific experiments.
Yeah, think of this as your kind of backstage pass to a science lab. We've looked at all sorts of intriguing stuff, from figuring out the colors in a Smartie, believe it or not.
Ha, really? Smarties.
Yeah, to reactions that, well, let's just say they're pretty dramatic, even making glue from plain old milk.
Okay, glue from milk, I'm intrigued. So we've got experiments with hidden light, ways to figure out what's actually in rocks.
Metal content and things like that.
The weird physics of rubber bands, which always surprises me.
Oh, absolutely.
That gooey world of slime. And then some, more fundamental stuff about acids, alcohols.
And even how chemists play detective to identify unknown substances.
So our mission today is really to be your guides through all this. We've waded through the instructions, the safety notes, the questions scientists ask.
Basically, we've done the legwork so you can get straight to the core science behind it all.
It's about understanding these everyday, or maybe not so everyday, phenomena without needing your own lab coat.
Precisely. A shortcut to the aha moments.
Okay, let's unpack this then.
Yeah.
Starting with something I think everyone can relate to, color. And Smarties. You mentioned Smarties chromatography.
That's the one. Chromatography, at its heart, it's just a really clever way to separate mixtures, to pull things apart.
Okay.
In this case, we're going to see that the single color you think you see on a Smartie, it's often actually a blend of different dyes.
Huh. So it's not just like one type of blue.
Not necessarily. This technique is actually fundamental in science.
Yeah.
Used everywhere, from developing medicines to checking water quality. It lets us isolate things.
Right. So the experiment itself, you take the color off the Smartie, dissolve it, put a spot on some paper.
Filter paper, usually.
And then you let water creep up the paper.
Exactly. And as the water moves, it picks up the dyes and carries them along. But here's the key bit. Some dyes stick to the paper more. Some dissolve in the water better.
Ah, so they travel at different speeds?
Precisely. The ones that like the water more and the paper less, they travel further up.
So you might start with one spot of color and end up with several different bands.
You got it. And the big question is, why do some dyes separate out like that, while maybe another color doesn't? And why do some travel, way further than others?
It comes down to the properties of the dye molecules themselves, I guess. How soluble they are, how sticky they are to the paper.
That's exactly it. Solubility in the water versus attraction or adsorption to the paper.
It's kind of mind-blowing that what looks like one simple color is actually a whole team effort.
Isn't it? And the experiment even suggests checking the ingredients on the Smarties packet afterwards.
Oh, cool. A little link to food science and labeling.
Yeah. Okay, so from pretty colors, let's shift gears to something a bit more energetic.
More dramatic, you said. What's this decomposition of magnesium silicide?
Right. So this one showcases a reaction that doesn't need much energy to get started, what chemists call low activation energy.
Like a tiny push gets it going?
Exactly. Think of it like a boulder right at the edge of the cliff, just a nudge. But the result here is quite spectacular.
Okay, you've got my attention. What happens?
Well, first you have to make the magnesium silicide. You heat magnesium powder and silicon powder together.
Okay.
Let it cool, crush it up carefully. And then the interesting part, you add this powder to some dilute acid.
Yeah.
And a gas called silane gets produced. And this gas, silane, it just bursts into flame spontaneously when it hits the air.
Whoa. Spontaneously. Like poof.
Poof, exactly. That's why the instructions are super strict on safety screen, fume hood, or really good ventilation, eye protection. It tells you you're dealing with something pretty reactive.
Yeah, no kidding. So there are chemical equations explaining this.
There are. First, the magnesium and silicon react when heated. Then that magnesium silicide reacts with the acid, technically the water in the acid-making silane gas.
And then the silane meets oxygen?
And boom, combustion. It burns to form silicon dioxide, basically sand and water.
Wow. And the experiment asks why silane does this so easily, but methane, which looks kind of similar chemically, doesn't.
Right. Methane needs a spark.
Yeah.
Right? Silane doesn't. It boils down to the bonds. The silicon-hydrogen bonds in silane are just weaker and more easily broken than the carbon-hydrogen bonds in methane.
So it's inherently less stable.
Pretty much. That instability leads right to that spontaneous combustion. It's a really powerful visual of chemical energy being released.
Definitely an aha moment. Okay, so reactions can release energy as heat and fire. What about releasing it as light? Chemiluminescence.
Exactly. Chemiluminescence, chemical light. Light produced directly from a chemical reaction, not because something's hot.
So like glow sticks.
That's the classic example. This experiment is often really simple. You just mix two solutions together, often solution A and solution B, in the dark.
And see if it glows.
Yep. See if that chemical reaction releases energy as visible light.
Simple but effective. And then it says you can add dyes, like fluorescein.
Yeah, that's a neat twist. You do the reaction again, but add a fluorescent dye. The energy from the initial reaction gets transferred to the dye.
Which then emits its own color of light.
You got it. It shows how energy can be transferred and re-emitted. The experiment asks you to think about real-world uses.
Well, glow sticks, obviously, but what else?
Think about forensic science liminal. Detecting traces of blood works this way. And some sensitive biological tests use chemiluminescence to detect tiny amounts of specific molecules. It's surprisingly versatile.
Amazing that chemicals mixing can just produce light. Okay, from creating light to figuring out what's in things, like rocks, determining copper in an ore.
Right. An ore is just rock that has enough valuable metal mixed in to be worth mining. But first, you need to know how much good stuff is actually there. Is it worth dotting up?
Makes sense. So how do you estimate the copper?
This method uses color. You grind up the ore sample, weigh it accurately, and then dissolve the copper out using sulfuric acid.
Okay, sulfuric acid. The instructions mention safety here too, right? Corrosive.
Oh yeah, very corrosive. And the reaction can fizz and spit, so you need proper protection. After dissolving, you filter out all the leftover rock bits that didn't dissolve.
The stuff you don't want.
Exactly. And if there was copper in the ore, the liquid you're left with to filtrate will be blue. Copper ions in solution are typically blue.
Ah, okay, so the more copper, the deeper the blue.
Precisely. The intensity of the blue color tells you about the concentration. So you compare the color of your filtered solution against a set of standard solutions where you know the exact copper concentration.
Like comparing paint swatches.
Kind of. You find the standard solution that matches your sample's color, and that gives you an estimate of the copper percentage in your original ore.
Clever. And the analysis questions it asks are good too. Like, what causes the blue color?
That's the dissolved copper ions interacting with water molecules.
And what got filtered out?
All the insoluble rock material, silica,
Yeah.
other minerals that don't dissolve in the acid, you need to get rid of that so you can see the blue color clearly.
Right. And how could you double check the result?
Good question. You could maybe use an instrument called a colorimeter for a more precise measurement, or maybe try dissolving the ore in a different way, or just repeat the whole thing carefully to ensure it's reproducible. Thinking about validation.
Always important in science. Okay, complete change of pace now. You mentioned glue from milk. Seriously.
Seriously. It's a brilliant example of kitchen chemistry, really. Extracting something useful from an everyday food. The key is a protein in milk called casein.
Casein. Okay, how do you get it out and make it sticky?
You start with skimmed milk, less fat interference.
Mm.
You add some ethanoic acid, which is basically just vinegar.
Plain old vinegar.
Yep. And you warm it gently while stirring. You'll start seeing little white bits forming.
Curdling.
Essentially, yes. The acid changes the pH, causing the casein protein molecules to sort of unravel and then stick together. They coagulate. These are the curds.
Okay, so you get solid bits.
Right. You let them settle, pour off the watery liquid. That's the whey.
A little Miss Muffet stuff.
Exactly. Then you filter the curds to get rid of more whey, maybe give them a quick rinse. Now you've got this sort of damp, cheesy casein solid.
But that's not glue yet.
Not yet. You add a bit of water back,
Yeah.
and then the other key ingredient, sodium hydrogen carbonate.
Baking soda.
That's the one. You mix that in, and you might notice some fizzing.
Why the baking soda?
Yeah.
And why the fizz?
Good questions.
Yeah.
The baking soda is a base, and it neutralizes any leftover vinegar, any acid that's still trapped in the casein. That acid-base reaction produces carbon dioxide gas.
Ah, the bubbles.
Those are the bubbles. And once that reaction's done, you've basically got casein glue. The experiment suggests you test how well it sticks paper or wood together.
Fascinating. And it asks why the vinegar, why the baking soda, getting you to think about the chemical steps.
Precisely. It's transforming a protein polymer casein using simple acid-base chemistry into an adhesive, seeing chemistry in action in the kitchen.
Very cool. Okay, from sticky stuff to stretchy stuff, rubber bands. This sounds intriguing, too.
Ah, yes, the physics of rubber bands. It starts with something you can try right now, actually.
Oh, yeah. What's that?
Take a decent rubber band, stretch it quickly, and immediately touch it to your lips. Notice the temperature. Then keep it stretched for a second, let it relax really quickly, and touch it to your lips again.
Okay, so stretch it quick, feels maybe a tiny bit warmer, let it snap back, feels cooler.
That's what most people feel.
Yeah.
It hints at energy changes. Now, the main experiment involves hanging a weight on a rubber band.
Just letting it dangle.
Yeah. Then you aim a hairdryer at the stretched rubber band and heat it up. But first predict, what do you think will happen to the length of the rubber band when you heat it?
Heat usually makes things expand, right? So I'd guess it gets longer.
That's the intuitive guess. But watch closely. When you heat the stretched rubber band, it actually gets shorter. It contracts.
No way. It shrinks when heated? That's bizarre.
It seems totally counterintuitive, doesn't it? But it's real. It connects to a principle called Le Chatelier's principle and thermodynamics.
Okay, break that down.
Stretching the rubber band is actually an exothermic process. It releases a tiny amount of heat, which is why it felt warm.
Right.
Le Chatelier's principle says systems try to counteract changes. So if you add heat to the stretched band, which released heat when stretched, it tries to do the opposite. It tries to absorb heat. And the process that absorbs heat for a rubber band is contracting.
Ah, so heating it makes it contract to absorb the heat.
Exactly. And contracting is endothermic. It absorbs heat, which is why it felt cool when you let it snap back quickly.
That makes sense.
No.
Sort of.
Yeah.
What's happening with the molecules?
It's about order and disorder entropy. In a relaxed rubber band, the long polymer chains are all jumbled up, very disordered. When you stretch it, you force them to line up, becoming more ordered.
Okay.
Systems naturally prefer disorder, higher entropy. So when you heat the stretched, ordered band, the molecules gain energy and wiggle more, wanting to go back to their preferred, tangled, disordered state. That collective movement causes the macroscopic band to contract.
Wow. So the weird shrinking is actually the molecules trying to get messy again?
In a nutshell, yes. It's a fantastic demonstration of polymer physics.
Definitely. Okay, from rubber bands to, well, another polymer phenomenon, slime.
Ah, slime. Always a crowd pleaser. This experiment shows you how to make it by cross-linking a polymer called polyvinyl alcohol, or PVA.
Isn't that in some types of glue?
It is. You mix a PVA solution with a borax solution. The borax acts as a cross-linker, kind of tying the long PVA chains together at various points, forming a network. You can add color too, of course.
And then the fun part is testing it.
Absolutely. The instructions say, try pulling it slowly. Then try pulling it sharply. Drop it. Hit it. Press it on a newspaper ink. See what happens if you add a little acid or base.
Okay, so what does happen? What's the aha moment with slime?
The key thing you'll notice is its weird behavior under stress. Pull it slowly, and it flows, stretches, acts like a very thick liquid.
Right.
But give it a sharp tug, or hit it, and it resists. It might even snap or feel quite solid for a moment.
So it's like a liquid and a solid.
Exactly. That's called viscoelasticity. It behaves differently depending on how quickly you apply force. That's the big takeaway. It flows over long time scales, but resists sudden forces.
Cool. And the ink test?
That can tell you about the slime's properties. Does it absorb water-based ink easily? Maybe less so as spirit-based inks. It hints at its chemical nature.
And the acid-base test?
Adding acid or base can disrupt those cross-links made by the borax. You might see the slime change consistency, maybe become more liquidy. And the question is, can you reverse it? Can you add something to bring it back?
Ah, showing that the cross-linking reaction might be reversible.
Potentially, yes.
Yeah.
It's a great hands-on way to feel how molecular structure, those cross-links, dictates the material's properties you can actually touch and stretch.
Definitely seems like fun. Okay, let's get into some more specific chemical properties now, starting with ethanoic acid again, our friend from the milk glue.
Right. Ethanoic acid, or acetic acid, in vinegar. It's described as a weak organic acid. The key feature is that carboxyl group, the next COH group.
So these tests are about seeing its acidic nature.
Yep. Standard acid tests, you test its pH with indicator paper. It'll be acidic, but maybe not pH 1 like a strong acid.
Okay.
Then you react it with sodium carbonate. You'd expect bubbles, right? Carbon dioxide.
Acid plus carbonate, yeah.
Then react it with sodium hydroxide, that's a base, so an acid-base neutralization, and react it with magnesium metal acids, react with active metals to produce hydrogen gas. You observe carefully what happens in each case.
And the experiment compares this to hydrochloric acid, a strong acid.
Exactly. It gives the equations for HCl reacting with the same thing, so you can directly compare. Does the ethanoic acid react as fast? Is the reaction as vigorous?
And it probably isn't because it's a weak acid.
That's what you'd expect.
Yeah.
And ask you to think about why. Why is ethanoic acid weaker?
What's the reason then?
It comes down to how much it breaks apart or ionizes in water. Strong acids like HCl basically split up completely,
Yeah.
releasing lots of hydrogen ions, H+.
Okay.
Weak acids like ethanoic acid only partially ionize. Only some of the molecules release their H+. So there's just a lower concentration of those reactive H+ ions available at any given moment.
Got it. Fewer active players in the game.
That's a good way to put it. Now, related but different. Alcohols.
Alcohols, like ethanol, the one in drinks,
Yeah.
characterized by that OH group.
Exactly, the hydroxyl group, OH. This section looks at key properties of ethanol.
What tests are involved here?
First, simple stuff. Does it mix with water? Check the pH of the mixture. Most simple alcohols mix well with water because that OH group is polar, like water.
Okay, then burning it.
Carefully, yes. Observing the flame. Ethanol is flammable, which is a key property. Safety first, obviously it's flammable and toxic if ingested.
Right, and then reacting it with something.
Yes, heating it gently with acidified potassium dichromate. That's an oxidizing agent. You look for a color change. The orange dichromate turning green is a classic sign that the alcohol has been oxidized. Maybe a change in smell, too.
Oxidize, meaning it reacts with the oxidizing agent.
Yes, the alcohol loses electrons, effectively. The experiment prompts you to think about uses based on these properties: solvent, fuel.
Right, and how it's made industrially.
Primarily fermentation of sugars, yeah.
And the reverse of oxidation.
That's reduction. It also asks for the equation for burning ethanol combustion. C2H5OH plus O2 gives CO2 and H2O. Balancing it is the trick.
Okay, so solubility, flammability, ability to be oxidized, key alcohol traits.
And finally, we get to the real detective work, identifying unknown salts.
Finding the chemical fingerprints, you called it? Figuring out the positive and negative ions in a mystery sample.
Exactly. This lays out a systematic approach. First, testing for anions, the negative ions.
Like chloride, sulfate, carbonate.
Those are common ones, yes. Plus bromide, iodide. There are specific tests using reagents like nitric acid, silver nitrate, barium chloride. You look for telltale signs.
Like a solid forming, a precipitate.
Right. Silver nitrate forms precipitates with chloride, bromide, and iodide, but they look slightly different, and they have different solubilities in ammonia solution, which helps distinguish them.
Okay.
Barium chloride test for sulfate ions gives a white precipitate. Adding acid to test for carbonate ions produces bubbles of CO2. It's all about adding the right reagent and observing carefully.
And then testing for the cations, the positive ions.
Similar idea. Often involves adding sodium hydroxide solution drop by drop, then in excess, and doing the same with ammonia solution.
Why those two?
They form metal hydroxide precipitates with many metal ions, but the precipitates have characteristic colors, and some dissolve if you add more reagent while others don't.
Ah, so the color and whether it dissolves tells you which metal might be present.
Exactly. Helps identify things like copper 2, blue precipitate, iron 2, dirty green, iron 3, rusty brown, lead 2, zinc, aluminium. These are often white, but differ in how they react to excess alkali or ammonia.
And there's a special test for ammonium ions.
Yeah, you warm the sample with sodium hydroxide. If ammonium ions are present, they release ammonia gas, which you can usually smell, or test with damp red litmus paper. It'll turn blue.
And flame tests. I remember those from school.
Always a highlight. Heating a sample in a Bunsen flame. Different metal ions give off characteristic colors when their electrons get excited and then fall back down.
Like sodium's bright yellow, potassium's lilac.
Exactly. Copper gives a blue-green, lithium a crimson-red, calcium an orange-red. The table provided lists these colors. It's another tool in the chemist's identification kit.
So anion tests, cation tests, flame tests, it's all about being systematic and recording what you see.
Absolutely. Careful observation and methodical work are key to cracking the chemical code.
Wow. That has been an absolutely incredible journey through, such a diverse range of experiments.
It really shows how much science is packed into seemingly simple things, doesn't it?
It really does. It drives home how much is going on under the surface, things we see every day. And hopefully, for you listening, this deep dive has been a really efficient way to kind of grasp these core ideas without needing Bunsen burners and safety goggles right now.
Absolutely. Consider it the condensed version. And the key takeaway, I think, is that the world around us is just full of these opportunities for exploration, for those little aha moments.
Yeah, these experiments, they're really just jumping off points, aren't they?
Definitely. Science isn't just about known answers. It's about asking the next question.
Okay, so here's something to mull over then. Pick one. Just one of the experiments we talked about, maybe the Smarties colors or the weird rubber band thing or making glue from milk, whatever caught your interest. And just think, how could you change it? If you were doing it, what else could you test? What other questions pop into your head now?
Yeah, what variables could you tweak? What other materials could you try?
Exactly. It's all about keeping that curiosity going, right?
Exactly.
Continuing your own sort of mini deep dives into the amazing world that's all around us.